Picture this: a lone, dimly glowing ember suspended in the endless black of space. It's not a newborn star blazing with youthful energy, but something far more mysterious. A white dwarf, the dense, fading core of a star that once shone brightly. This cosmic relic isn't just a remnant of stellar death. It's a time capsule, a silent witness to billions of years of galactic history. Imagine holding a book written in starlight, its pages filled with the secrets of ancient cosmic events. That's exactly what white dwarfs are: celestial archivists, preserving the universe's past in their slowly cooling hearts. What if I told you these stellar fossils hold clues to the very fabric of our galaxy? Every white dwarf is like a cosmic detective, its composition revealing stories of long-gone stars, violent collisions, and the delicate dance of elements that shaped everything around us. The heavier elements trapped in their atmospheres, the faint whispers of light they emit, these aren't just random details. They're pieces of a puzzle, fragments of a grand narrative about how galaxies like ours evolved over eons. So, what can these ancient stars teach us? That's the journey we're about to take together. We'll unravel how white dwarfs act as cosmic record keepers, their layers of helium and hydrogen hiding tales of stellar births and deaths. We'll explore how they preserve the fingerprints of long-lost supernovae, and how their slow, steady fade into darkness is anything but quiet. It's a treasure trove of data waiting to be decoded. By the end of this, you'll see these unassuming stellar remnants in a whole new light, not as endpoints, but as keys to understanding the universe's deepest mysteries. Ready to dive in, the stars are waiting to tell their stories. Every star begins its life as a whisper in the darkness, a dense pocket of gas and dust collapsing under its own gravity, igniting the nuclear furnace at its core. Picture a stellar nursery, one of those vast, glowing nebulae where new stars are born. Over millions of years, gravity pulls these cosmic ingredients together until the pressure and heat become so intense that hydrogen atoms fuse into helium, releasing the energy that makes stars shine. This is the moment a star is truly born, bursting into the universe with light and heat. But stars, like all things, don't last forever. How they live and how they die depends entirely on their size. Take a massive star many times heavier than our Sun. It burns through its nuclear fuel at a furious pace, shining brilliantly but briefly before meeting a spectacular end. When it runs out of fuel, the core collapses in a violent explosion, a supernova, scattering its enriched remains across space. These cataclysmic deaths forge the heaviest elements in the universe, from gold to uranium, seeding future generations of stars and planets. Now consider a star like our Sun, a far quieter, more patient cosmic traveler. For billions of years, it steadily fuses hydrogen into helium, maintaining a delicate balance between gravity's inward pull and the outward pressure of nuclear reactions. But even this stable existence has an expiration date. As the hydrogen dwindles, the core contracts, heating up until helium itself begins to fuse into carbon and oxygen. The outer layers swell, transforming the star into a red giant, hundreds of times larger than before. Eventually, these outer layers drift away, leaving behind only the star's exposed core, a white dwarf. This is where the story gets truly fascinating. A white dwarf is unimaginably dense, packing a sun's worth of mass into an Earth-sized sphere. A single teaspoon of its material would weigh tons. Yet despite its incredible density, it no longer generates energy through fusion. Instead, it slowly cools over billions of years, radiating away its remaining heat like a dying ember. But here's the remarkable part: this cooling process isn't just an end, it's a preservation. The elements locked inside, the traces of heavier atoms captured in its atmosphere, these are the fingerprints of the star's life, the echoes of its journey through cosmic time. And that's the key to understanding why white dwarfs are such extraordinary historians. They don't just tell us about their own past, they hold records of the galaxy itself. Every atom, every subtle variation in their composition is a clue waiting to be deciphered. The universe writes its history in starlight and white dwarfs. They're the keepers of its most ancient archives. To truly grasp the astonishing nature of white dwarfs, we need to step into the realm of extreme physics. Imagine crushing an entire star, something with the mass of our Sun, into a sphere no larger than Earth. The result is so dense that a single teaspoon of its material would weigh as much as an elephant here on our planet. This mind-bending compression defies everyday intuition, but it's the reality of these stellar remnants. What keeps them from collapsing further into an even more exotic object like a neutron star or black hole? The answer lies in a quantum mechanical phenomenon called electron degeneracy pressure. At these incredible densities, electrons are packed so tightly they can't occupy the same quantum states, creating an outward force that counteracts gravity's relentless pull. It's not fusion propping up the star anymore, it's the sheer refusal of electrons to be squeezed closer together, a cosmic standoff that can last for trillions of years. This delicate balance gives white dwarfs their stability, even as they slowly radiate away their heat over eons, fading like dying coals in a fireplace. One of the most famous white dwarfs, Sirius B, orbits the brightest star in our night sky, Sirius A. Though it's roughly the same mass as our Sun, Sirius B is so compact that its diameter is less than that of Earth. If you could place it next to our planet, it would look like a tiny, shimmering marble, but with a gravitational pull nearly 350,000 times stronger. That's the paradox of white dwarfs. Their unassuming size hides unimaginable density, a testament to the extremes of stellar evolution, but their true value lies in what they preserve. As these stellar embers cool, their atmospheres become layered time capsules. Heavier elements like carbon, oxygen, and even traces of metals sink toward the core, while lighter elements like hydrogen and helium float to the surface. By studying these layers, astronomers can reconstruct the star's life story, what it consumed, how it evolved, and even the interstellar material it swept up during its journey. It's like reading the diary of a star, written in the language of atomic spectra. The composition of a white dwarf isn't just a record of its own past, it's a snapshot of galactic chemistry. Some contain unexpected metals elements that shouldn't exist on their surfaces unless they were pulled from a companion star or a passing asteroid. Others show signs of planetary debris, hints that entire worlds may have once orbited them before being torn apart in the star's final, violent phases. These cosmic breadcrumbs tell us not just about individual stars, but about the dynamic, ever-changing environment of our galaxy. Every white dwarf is a silent historian, its elements whispering secrets about the universe's grand narrative. Think of a white dwarf's atmosphere like the rings of an ancient tree. Each layer tells a story. Over its lifetime, a star fuses lighter elements into heavier ones, forging carbon, oxygen, and beyond in its core. When it sheds its outer layers and becomes a white dwarf, these freshly forged elements rise to the surface, mixing with any material the star may have absorbed from its surroundings. The result, a celestial fingerprint unique to that star's history. But how do these stellar fossils actually preserve galactic history? It all comes down to gravity. A white dwarf's intense gravitational pull acts like a cosmic trap, capturing and holding onto elements that would otherwise drift away into space. Hydrogen and helium float to the top, while heavier metals like calcium, iron, even gold sink deeper over time. This sorting process creates a layered record, almost like pages in a book. Astronomers read these layers by analyzing the light white dwarfs emit, decoding which elements are present and in what amounts. A sudden spike in silicon or nickel, that could be evidence of a long-ago collision with a rocky planet or asteroid, an unexpected abundance of carbon. Perhaps a clue about how the star burned its fuel in its final phases. What makes white dwarfs such extraordinary archivists is their stillness. Unlike active stars which churn and mix their interiors, white dwarfs change very little over time. The elements they hold onto aren't diluted or destroyed, they're frozen in place, preserved with near-perfect fidelity. It's as if the universe pressed pause, leaving behind a pristine snapshot of a star's final moments. And here's where it gets even more fascinating. Some white dwarfs have been found with traces of planetary debris in their atmospheres. Imagine a star in its red giant phase swallowing nearby planets whole. As it collapses into a white dwarf, fragments of those worlds' rocks, metals, even water, are left suspended in its outer layers. By studying these traces, scientists can piece together not just the life of the star, but the fate of the planets that once orbited it. It's like cosmic archaeology, uncovering lost civilizations only instead of pottery shards. We're analyzing starlight for traces of vaporized mountains and oceans. This is why white dwarfs are more than just dead stars. They're galactic librarians cataloging the chemical history of the universe. Every element they hold is a clue, a breadcrumb leading us back through time to understand how stars live, die, and shape the cosmos around them. Deep within the crystalline structure of a white dwarf, the universe has etched its memoirs in atoms. These stellar remnants don't just fade quietly into the dark. They hoard cosmic evidence like meticulous archivists, their composition revealing chapters of galactic history that would otherwise be lost to time. Take heavy metals, for instance. When astronomers detect traces of iron, calcium, or even uranium in a white dwarf's atmosphere, they're not just seeing random elements. They're uncovering the aftermath of ancient supernova violent explosions that seeded the galaxy with these materials billions of years ago. Each atom is a breadcrumb leading back to a specific moment in cosmic history, a clue about the violent deaths of massive stars that once illuminated the darkness. Then there's the planetary debris, fragments of shattered worlds found suspended in the atmospheres of some white dwarfs. Imagine a star in its final throes as a red giant, voraciously consuming the planets that once orbited it. Rocky bodies, ice giants, even entire oceans, all vaporized and absorbed into the star's outer layers. As the star collapses into a white dwarf, these materials don't vanish. They linger, suspended like dust in a sunbeam, waiting to be detected. By analyzing the ratios of elements like magnesium, silicon, and oxygen, scientists can reconstruct the composition of those long-dead planets. It's as if the white dwarf has preserved the ruins of an alien solar system, offering us a glimpse into what kinds of worlds might have existed in the galaxy's youth. But how do we decode these cosmic messages? The answer lies in spectroscopy, a technique as close to wizardry as modern astronomy gets. When light from a white dwarf passes through a telescope, it's split into a spectrum, a rainbow of colors punctuated by dark lines. Each line corresponds to a specific element, like a barcode revealing the star's chemical makeup. A spike in carbon might hint at a star that burned its fuel in an unusual way, while an abundance of nickel could point to a cataclysmic collision with a metallic asteroid. Spectroscopy transforms starlight into a language we can read, turning abstract gleams into detailed stories of cosmic events. What makes these records so invaluable is their role in mapping galactic evolution. White dwarfs aren't just isolated relics, they're pieces of a vast puzzle. By comparing their compositions across different regions of the galaxy, astronomers can trace how elemental abundances have changed over time. A cluster of white dwarfs rich in certain metals might mark the site of an ancient supernova blast wave, while another group with peculiar ratios of lighter elements could reveal how interstellar gas was recycled into new generations of stars. It's like assembling a timeline of the Milky Way's chemical history, one white dwarf at a time. And here's the profound implication: these fading embers are more than endpoints. They're bridges connecting us to the universe's past. Every heavy metal, every speck of planetary dust, every spectral line is a testament to the dynamic, ever-changing nature of the cosmos. White dwarfs don't just hold records, they hold the keys to understanding how galaxies grow, how planets form, and ultimately, how the universe writes its own story. White dwarfs are more than just relics, they're time machines, offering us a direct line to the universe's distant past. Unlike stars still burning brightly, these fading embers change so slowly that their current state reflects conditions from billions of years ago. Their cooling rates are glacial, dropping in temperature by mere degrees over millennia. This near standstill means the elements locked within them haven't been disturbed or diluted, preserving a pristine record of the galaxy's chemical makeup during their formation. It's as if we've discovered a cosmic freezer, perfectly preserving ingredients from the universe's early kitchen. Take the oldest known white dwarfs, some over 10 billion years old. Their atmospheres contain barely any heavy elements, a telltale sign they were born when the universe was still young and pristine, before generations of supernovae enriched the cosmos with metals. By contrast, younger white dwarfs often show traces of silicon or iron, evidence they formed later, after violent stellar explosions had scattered these elements across the galaxy. It's like comparing a first edition book to a revised printing. The differences reveal how the story of star formation evolved over time. One remarkable discovery came from studying white dwarfs in globular clusters, ancient gatherings of stars that orbit our galaxy. These white dwarfs are so old that their light carries signatures of the universe's first stellar generations. Their atmospheres revealed unexpected patterns of oxygen and carbon, suggesting the earliest stars may have burned their fuel in ways we don't see today. It's a window into a lost chapter of cosmic history, showing us that star formation wasn't always the orderly process we observe now. So how do scientists extract these stories from faint points of light years away? The key lies in combining cutting-edge technology with patient observation. Advanced telescopes like Hubble and James Webb capture the white dwarf's faint glow, while spectrographs break that light into detailed fingerprints of elemental composition. But the real magic happens in the data. Sophisticated models simulate how these stars cool and settle, allowing researchers to backtrack from today's observations to the conditions of the distant past. It's cosmic detective work, piecing together clues written in atomic structures and thermal emissions. What makes this approach so powerful is its ability to cross-check other methods of studying galactic history. White dwarfs serve as anchors for our understanding, providing ground truth that complements theories based on galaxy simulations or observations of distant, young stars. When multiple lines of evidence align, when the composition of an ancient white dwarf matches predictions from models of the early universe, it's like finding the missing piece of a jigsaw puzzle. locking our cosmic timeline into place. The implications stretch far beyond stellar archaeology. By revealing how element production has changed over billions of years, white dwarfs help explain why planets like Earth have the mix of metals necessary for life. They show us that the universe's chemical evolution isn't just background history, it's the foundation for everything we see around us, from the iron in our blood to the silicon in our computer chips. Each white dwarf is a witness to this grand transformation, a silent observer that's been keeping score since before our solar system existed. As we peer deeper into their fading light, we're not just studying dead stars, we're learning to read the universe's autobiography, written in the language of cooling embers and elemental whispers. The next time you look up at the night sky, remember, some of those faint points of light aren't just stars, they're time capsules holding stories older than the Earth itself. Spectroscopy transforms starlight into a cosmic Rosetta Stone, allowing astronomers to read the hidden language of white dwarfs. When light from one of these stellar remnants passes through a telescope, it doesn't arrive as a pure, unbroken beam. Instead, it carries subtle gaps, dark lines, interrupting the rainbow of colors like missing teeth in a comb. These absorption lines are the fingerprints of elements, each one corresponding to a specific atom in the white dwarf's atmosphere. Iron leaves its mark at certain wavelengths, calcium at others, and so on across the periodic table. By measuring where these lines appear and how deep they are, scientists can reconstruct the exact chemical makeup of a star millions of light years away. The process begins with an instrument called a spectrograph, which acts like a prism on steroids. It splits incoming starlight into an incredibly detailed spectrum, revealing patterns so precise they could distinguish between the light signatures of two different brands of street lamps. For white dwarfs, this precision is crucial. Their faint glow means every photon counts, and their dense atmospheres create absorption lines so narrow that only the most advanced instruments can resolve them. That's where telescopes like Hubble come in. Orbiting above Earth's distorting atmosphere, Hubble's Space Telescope imaging spectrograph has captured spectra of white dwarfs with clarity ground-based telescopes could only dream of. Its observations revealed unexpected metals like titanium and chromium in stars where they shouldn't exist, clues that these white dwarfs might have cannibalized rocky planets. Recent advancements have taken this detective work even further. The James Webb Space Telescope's infrared capabilities peer through cosmic dust that obscures visible light, uncovering spectral details from white dwarfs hidden behind nebulous veils. Meanwhile, machine learning algorithms now sift through mountains of spectral data, spotting patterns human eyes might miss. One surprising discovery came from this combination of technology and ingenuity. Some white dwarfs show traces of water in their spectra. Not liquid oceans, of course, but vaporized ice from comets or dwarf planets that spiraled too close and were torn apart by the star's gravity. Perhaps the most startling spectral findings involve elements that shouldn't be there at all. Certain white dwarfs exhibit absorption lines for heavy metals like gold and uranium elements so dense they should sink below the star's observable layers within centuries. Their presence suggests ongoing accretion, as if these stellar fossils are still feeding on planetary debris billions of years after their formation. Other spectra reveal bizarre mixtures of elements that don't match any known planetary composition, hinting at exotic worlds unlike anything in our solar system. Each new spectral line is another piece in the puzzle, another chapter in the galaxy's autobiography written in atomic ink. What makes these discoveries so revolutionary isn't just what they tell us about individual stars. When combined, spectra from thousands of white dwarfs form a chemical census of our galactic neighborhood, showing how element abundances vary across space and time. They reveal that the Milky Way's history is messier than we thought, full of stellar collisions, galactic cannibalism, and planetary systems being born, dying, and being recycled in an endless cosmic dance. The light from these fading embers doesn't just illuminate their own stories, it shines a light on the universe's grand narrative, one spectral line at a time. Heavy metals shouldn't linger on the surface of a white dwarf. That's the first clue something extraordinary is happening. In these dense stellar remnants, gravity acts like a cosmic sieve, pulling heavier elements like iron, nickel, and gold downward so quickly they should vanish from view within centuries. Yet when astronomers point their telescopes at certain white dwarfs, they find these very metals gleaming in their spectra. It's as if the stars have been dusted with cosmic glitter, a shimmering residue that points to a dramatic past. The explanation: these white dwarfs are cosmic graveyards, their atmospheres polluted by the shattered remains of planets that once orbited them. Picture the final act of a planetary system. As a star like our Sun nears the end of its life, it swells into a red giant, its outer layers expanding to engulf nearby worlds. Mercury, Venus, even Earth, all would be vaporized in this stellar inferno. But farther out, asteroids and dwarf planets might survive the initial expansion, only to meet a more gruesome fate later. When the star collapses into a white dwarf, its gravitational pull becomes so intense that any surviving rocky bodies are vulnerable. A stray asteroid venturing too close would be torn apart by tidal forces, its debris stretched into a glowing ring before raining down onto the star's surface. This is the source of those mysterious metals, the literal ashes of dead worlds. The evidence is etched in light. When astronomers analyze the spectra of these metal-polluted white dwarfs, they're not just seeing random elements, they're reading the composition of obliterated planets. Take JD 361, a white dwarf located about 160 light-years away. Its atmosphere contains traces of oxygen, magnesium, and iron in ratios that match the expected makeup of a rocky planet's crust. Another, named WD 1145, shows signs of vaporized water mixed with rocky material, suggesting it once consumed icy bodies similar to comets or moons. These aren't just abstract detections, they're chemical autopsies, revealing what these lost worlds were made of before they were ripped apart. What makes these findings revolutionary isn't just the destruction, it's the preservation. The way metals are distributed in a white dwarf's atmosphere acts like a cosmic blender, homogenizing the debris into a detectable signature. By measuring the abundance of elements like silicon versus iron, scientists can reconstruct whether the ingested material came from a planet's core, mantle, or crust. Some white dwarfs even show signs of continental crust-like material, hinting that their former planets might have had geological processes similar to Earth's. It's an eerie thought. We're studying the guts of worlds that died billions of years ago, their remains preserved in the stellar equivalent of formaldehyde. The implications stretch far beyond morbid curiosity. These polluted white dwarfs are giving us our first direct look at the building blocks of exoplanetary systems, not just their current states, but their ultimate fates. Before this, astronomers studying exoplanets had to rely on indirect methods, like measuring the dimming of starlight as planets transited their suns. Now they can examine planetary material up close, atom by atom, in the atmospheres of white dwarfs. It's like swapping a blurry photograph for a high-resolution lab analysis. Already, this approach has revealed planetary systems far more diverse than our own, with compositions ranging from super-Earths rich in carbon to worlds with mantle materials unlike anything in our solar system. Perhaps the most profound revelation is how common these planetary graveyards seem to be. Studies suggest up to 50% of white dwarfs show signs of rocky debris in their atmospheres, implying that planet formation and destruction is a universal process. That means what happened to these systems could one day happen to ours. When our sun becomes a white dwarf billions of years from now, the inner planets may share the same fate, their atoms forever preserved in its glowing ember. But there's a twist. Not all destruction is permanent. The same processes that tear planets apart might also seed new ones. Heavy metals released into space by white dwarfs eventually mix with interstellar gas, becoming raw material for future generations of stars and planets. The iron in your blood, the calcium in your bones, some of those atoms might have once belonged to a world that orbited a long-dead star. White dwarfs aren't just endpoints, they're recyclers, turning the rubble of old worlds into the foundations of new ones. So the next time you hear about a metal-polluted white dwarf, remember, you're not just looking at a dead star, you're seeing the ghostly fingerprints of planets that once were, a testament to the dynamic, ever-changing nature of the cosmos. These stellar fossils don't just tell us about the past, they hint at the future, revealing the cyclical nature of cosmic creation and destruction that shapes everything from distant galaxies to the atoms in our own bodies. When a star like our Sun reaches the end of its life, it doesn't go quietly. Its final act is a spectacular transformation, one that reshapes its entire planetary system. Imagine a star that once burned steadily for billions of years suddenly swelling into a monstrous red giant, its outer layers expanding outward like a fiery tide. Mercury, Venus, and even Earth would be swallowed whole, vaporized in an instant by temperatures hot enough to melt rock into gas. The inner solar system becomes a furnace, worlds erased as if they were never there. But farther out, the story changes. Planets like Mars, Jupiter, and beyond might survive the star's expansion, at least temporarily. As the red giant's outer layers drift away, they create a swirling nebula of gas and dust, while the star's core collapses into a white dwarf. This newborn stellar remnant is tiny but unimaginably dense, packing a sun's worth of mass into a sphere no larger than Earth. Its gravitational pull remains fierce, enough to perturb the orbits of any surviving planets. Some might be flung into deep space, becoming rogue worlds drifting between the stars. Others could spiral inward, torn apart by tidal forces until their debris forms a glowing disk around the white dwarf, a cosmic graveyard of planetary remains. Yet there's a twist in this tale of destruction. Even in the aftermath, new possibilities emerge. White dwarfs, though dim, still emit heat, and where there's heat, there's the potential for life. Astronomers have theorized about second-generation habitable zones around these stellar embers. A planet orbiting at just the right distance, close enough to stay warm, but not so close to be ripped apart, could maintain liquid water for billions of years. Imagine a world where the sun is a pale, Earth-sized orb in the sky, casting faint blue-white light over frozen oceans slowly thawing in the star's residual warmth. This isn't just speculation. Observations of white dwarfs with unusual infrared emissions suggest some might still host debris disks or even surviving planets. In 2020, researchers spotted a Jupiter-sized candidate orbiting a white dwarf in a wide orbit, hinting that gas giants can endure these cataclysms. Even more intriguing are the traces of water and organic molecules found in the atmospheres of certain white dwarfs' chemical fingerprints of icy bodies that may have once been habitable moons or dwarf planets. What does this mean for our understanding of planetary survival? It shatters old assumptions. We used to think a star's death was the end for its planets, but now we see it as a cosmic reset, a violent rebirth where some worlds perish, others adapt, and a lucky few might even give life a second chance. If planets can outlast their stars, then the universe could be filled with ancient, hidden worlds orbiting these stellar fossils, their histories waiting to be uncovered. And here's the profound implication: our own solar system will face this fate. 5 billion years from now, the sun will expand, scorching the inner planets before collapsing into a white dwarf. Earth may not survive, but Jupiter's moons, or even a captured rogue planet, could find themselves in a new habitable zone, warmed by the sun's fading glow. The cycle of destruction and renewal isn't just happening out there, it's written into our future. White dwarfs aren't just relics of the past, they're windows into the resilience of planetary systems, proving that even in death, stars can leave behind the seeds of new beginnings. Could life endure the death of a star? It's one of the most haunting questions in astrobiology, and white dwarfs might hold the answer. Picture a world orbiting one of these stellar remnants, bathed in its pale, ghostly glow. The surface temperature of a young white dwarf can hover around 5,000 degrees Celsius, similar to our sun, but its tiny size means it emits only a fraction of the light. For a planet to stay warm enough for liquid water, it would need to orbit incredibly close, perhaps within 1 million miles. That's tighter than Mercury's orbit around our sun, raising a cascade of challenges. Tidal forces could lock the planet's rotation, leaving one side scorched and the other frozen. Radiation from the white dwarf's violent past might have stripped away any atmosphere. Yet, against all odds, life might find a way. Recent simulations suggest a surprising possibility: planets migrating inward after the star's red giant phase. Imagine a world like Jupiter's moon Europa, ejected from its original orbit and drifting closer to the white dwarf. If it carried subsurface oceans, tidal heating from the star's gravity could keep those waters liquid for billions of years. Even more intriguing, studies of white dwarf atmospheres have detected elements like nitrogen and carbon, key ingredients for life, sometimes in ratios resembling those found on Earth. These discoveries hint that the building blocks of biology might persist or even reorganize in these extreme environments. The real breakthrough came in 2022, when astronomers spotted a potential giant planet orbiting WD 1856 plus 320, a white dwarf just 80 light-years away. While not in the habitable zone itself, its existence proves large planets can survive stellar evolution. Smaller, rocky worlds might too, especially if they formed from debris left after the star's death. These second-generation planets could inherit water and organic molecules from shattered comets, creating entirely new habitats in the ashes of the old system. What makes white dwarfs uniquely valuable to astrobiology isn't just their potential to host life, it's their stability. A white dwarf's energy output changes so slowly that a habitable zone could remain temperate for up to 8 billion years, dwarfing the lifespan of most main sequence stars. That's an eternity for life to emerge or adapt. Compare that to red dwarfs, where habitable planets face violent flares, or giant stars that burn out too quickly. White dwarfs offer a quiet, enduring haven, their steady light a beacon for civilizations that outlive their suns. This reshapes how we search for extraterrestrial intelligence. SETI researchers have begun scanning white dwarf systems for artificial radio signals, theorizing that advanced civilizations might migrate to these long-lived stars as their home suns fade. Even more compelling, the atmospheres of white dwarfs could betray technosignatures, industrial pollutants, or artificial gases that wouldn't occur naturally. A single detection could rewrite our place in the cosmos, proving that life isn't just a fleeting spark, but a force capable of enduring stellar apocalypses. The lesson from these stellar fossils is profound. Death doesn't always mean extinction. It can be a transformation, a reset that creates new opportunities in the wreckage of the old. Whether through migrating planets, subterranean oceans, or civilizations clinging to existence, white dwarfs teach us that life's tenacity might far exceed our wildest assumptions. As we peer into their faint light, we're not just studying the end of stars, we're glimpsing the resilience of biology itself, and the possibility that even in the coldest corners of the universe, life finds a way to endure. Galactic archaeology might sound like the plot of a sci-fi epic, but it's a real scientific discipline, and white dwarfs are its most valuable artifacts. Think of these stellar remnants as cosmic breadcrumbs scattered across the Milky Way. Each one's location, motion, and chemical makeup tells a story about where and how it formed, painting a picture of our galaxy's turbulent past. Unlike active stars which migrate over time, white dwarfs are like celestial fossils, preserving the conditions of their birth in their very structure. By studying their distribution, astronomers can trace the Milky Way's ancient star-forming regions, uncovering chapters of galactic history that would otherwise be lost. Take the galaxy's halo, a sparse outer region filled with some of the oldest stars in existence. White dwarfs found here often have pristine atmospheres, nearly devoid of heavy metals, a sign they were born when the universe was still young and chemically simple. Their orbits, looping far above the galactic plane, suggest they originated in smaller dwarf galaxies that merged with the Milky Way billions of years ago. These stellar time capsules are evidence of the galaxy's cannibalistic past, revealing how it grew by consuming its neighbors. Contrast them with white dwarfs in the crowded galactic disk, many of which show traces of iron and silicon. These younger remnants hint at eras when supernova explosions enriched the Milky Way with heavier elements, paving the way for rocky planets and perhaps life. But the real power of white dwarfs lies in their connection to dark matter, the invisible glue holding galaxies together. Since white dwarfs emit no energy through fusion, their motion is governed purely by gravity, including the gravitational pull of dark matter. By mapping their velocities and trajectories, scientists can infer the distribution of this mysterious substance. One groundbreaking study used the subtle wobbles of white dwarfs in the Milky Way's outskirts to detect dark matter's gravitational fingerprints, offering clues about its elusive nature. It's like using the sway of lanterns in a dark forest to map unseen terrain. What ties all these threads together is time. White dwarfs don't just record where events happened, they reveal when. Their cooling rates act as cosmic clocks, allowing astronomers to date ancient stellar populations with precision, a cluster of white dwarfs all cooling at similar rates. That's evidence of a single, dramatic burst of star formation billions of years ago. A lone white dwarf with an unusually cold temperature. It might be a relic from the Milky Way's earliest days. By combining these timelines with chemical and positional data, researchers are piecing together a narrative of our galaxy's evolution, from its chaotic infancy to its modern spiral structure. The implications stretch beyond astronomy. Understanding how the Milky Way assembled itself helps explain why Earth exists where it does, in a relatively quiet suburban neighborhood of the galaxy. It shows us that galaxies aren't static sculptures but dynamic, ever-changing systems, shaped by collisions, explosions, and the invisible hand of dark matter. And white dwarfs, those fading embers of dead stars, are the key to reading this grand story, one that's still being written, with every new observation adding another line to the Milky Way's autobiography. Some white dwarfs glow faintly with the light of the universe's dawn. These ancient stellar remnants are among the oldest objects we've discovered, with ages approaching 13 billion years, nearly as old as the cosmos itself. Their dim, steady light isn't just a relic of stellar death. It's a stopwatch ticking away the eons since the first stars flickered to life. How do we know their age? The answer lies in their cooling curves. Unlike active stars which generate heat through fusion, white dwarfs simply radiate away their residual warmth, fading like a forgotten ember. The rate at which they cool is astonishingly predictable, governed by the laws of thermodynamics and quantum physics. By measuring their temperature and luminosity, astronomers can calculate how long they've been cooling, effectively turning each one into a cosmic clock. One of the oldest known white dwarfs, catalogued as WD Jones 1342 + 420, offers a striking example. Its temperature hovers just above 3,000 degrees Celsius, scorching by human standards, but frigid for a stellar remnant. Based on its cooling rate, researchers estimate it formed within the first billion years after the Big Bang. That makes it a fossil from the era when galaxies were first assembling, a silent witness to the universe's wild youth. Its atmosphere contains almost no heavy elements, a pristine signature of a time before supernova had peppered the cosmos with metals. Studying stars like this is like finding a cave painting from the dawn of human history, except this artwork is written in hydrogen and helium, the universe's original pigments. But these ancient white dwarfs aren't just timekeepers, they're also cosmic validators. Their existence and properties align strikingly with predictions from Big Bang cosmology. Take the cosmic microwave background, the afterglow of the universe's birth. The ages inferred from white dwarf cooling rates match the timeline derived from that primordial radiation, creating a consistent narrative of cosmic evolution. It's as if the universe left us two independent clocks, one etched in starlight, the other in microwaves, and they're ticking in perfect synchrony. This convergence of evidence gives astronomers confidence that our understanding of the universe's early moments is fundamentally sound. Yet these stellar elders also pose profound puzzles. Some exhibit cooling patterns that defy expectations, lingering at certain temperatures longer than models predict. One theory suggests this anomaly could be caused by crystallization, a phase transition where carbon and oxygen in the white dwarf's core arrange into a lattice structure, releasing latent heat and slowing the cooling process. If confirmed, it would mean the oldest white dwarfs aren't just featureless spheres of degenerate matter, but intricate cosmic objects with complex internal structures. Others show unexpected traces of hydrogen in their atmospheres, hinting at reservoirs of primordial gas surviving from the universe's infancy. Perhaps most tantalizing are the outliers white dwarfs with compositions so bizarre they challenge our ideas about early star formation. A few exhibit extreme ratios of helium to hydrogen, suggesting they might be remnants of the universe's very first stars, which theorists believe were massive, short-lived, and chemically pristine. Finding these stellar ancestors would be like discovering the missing link in cosmic evolution, bridging the gap between the Big Bang's simplicity and the chemical richness of today's universe. Every ancient white dwarf we study adds another piece to this puzzle, helping us understand how the cosmos transformed from a sea of hydrogen and helium into the complex, galaxy-filled expanse we see today. What makes these discoveries so revolutionary isn't just what they tell us about the past, it's how they reshape our view of cosmic timescales. By anchoring our measurements to these stellar chronometers, we've refined estimates of the universe's age to unprecedented precision. They've also revealed that some globular clusters, dense gatherings of ancient stars, are hundreds of millions of years older than previously thought, pushing back the timeline of galaxy formation. As we peer deeper into space with next-generation telescopes, each new ancient white dwarf we uncover will sharpen our view of cosmic history, turning faint points of light into keys that unlock the universe's deepest secrets. White dwarfs and neutron stars might both be stellar remnants, but they represent entirely different chapters in the life and death of stars. Imagine the difference between a fading ember and a crushed diamond. One is dense, but the other defies comprehension. When a star like our Sun dies, it leaves behind a white dwarf, packing a sun's worth of mass into an Earth-sized sphere. But when a much more massive star explodes in a supernova, its core can collapse into something far more extreme. A neutron star, where matter is compressed so tightly that protons and electrons merge, forming a city-sized orb of pure neutrons. A single teaspoon of neutron star material would weigh billions of tons, dwarfing even the incredible density of a white dwarf. The way these objects form tells two very different cosmic stories. White dwarfs are the peaceful end for stars like our Sun, their outer layers drifting away to form planetary nebulae, while the core settles into a slow, quiet cooling process. Neutron stars, on the other hand, are born in violence, the result of supernovae so powerful they briefly outshine entire galaxies. Some neutron stars spin hundreds of times per second, emitting beams of radiation that sweep across space like cosmic lighthouses. These pulsars are a far cry from the steady glow of white dwarfs, which lack the magnetic fields or rotation speeds to produce such dramatic signals. Yet when it comes to studying galactic history, white dwarfs have a unique advantage: their stillness. Neutron stars are dynamic, their intense magnetic fields and rapid spins altering their surroundings in ways that can obscure their origins. White dwarfs, by contrast, change so slowly that their composition remains pristine, preserving a clear record of the elements they've accumulated over billions of years. While neutron stars reveal the universe's most extreme physics, white dwarfs offer something equally valuable: a window into the quieter, but no less important, processes that shape galaxies. What makes white dwarfs truly special are the phenomena unique to them. Take Type Ia supernova, for example. These staggeringly bright explosions occur when a white dwarf in a binary system steals enough material from its companion to cross a critical mass threshold, triggering a runaway thermonuclear reaction. These standard candles help astronomers measure cosmic distances, proving the universe is expanding at an accelerating rate. Neutron stars can collide, creating ripples in space-time, but only white dwarfs give us these perfectly timed stellar explosions, each one a calibrated beacon in the dark. Then there's crystallization, the process where a white dwarf's core slowly solidifies into a lattice of carbon and oxygen, like a cosmic diamond forming over eons. This gradual transformation releases latent heat, subtly altering the star's cooling curve and giving astronomers another clue to its age and history. No neutron star exhibits this kind of metamorphosis. Their interiors remain a soup of exotic particles hidden behind impenetrable gravity. So while neutron stars show us the universe's extremes, white dwarfs reveal its endurance. They're the patient archivists, the keepers of long-term records, their faint light encoding billions of years of galactic evolution. Whether it's the debris of shattered planets in their atmospheres or the precise timings of their explosive deaths, these stellar fossils offer something neutron stars cannot: a chronicle of the universe's quieter but equally profound transformations. Not all white dwarfs fade quietly into the dark. Some meet a far more spectacular fate, a cataclysmic explosion so brilliant it can outshine entire galaxies. These are Type Ia supernova, the universe's ultimate fireworks, born when a white dwarf crosses a critical threshold known as the Chandrasekhar limit. Picture a stellar pressure cooker. As a white dwarf in a binary system siphons gas from its companion star, its mass creeps upward. Most of the stolen material burns away in runaway fusion reactions, but if the white dwarf reaches approximately 1.4 times the mass of our Sun, electron degeneracy pressure, the quantum force that's been holding it up suddenly fails. In an instant, the core collapses, temperatures skyrocket, and carbon ignites like a bomb. What follows isn't just an explosion. It's a thermonuclear detonation that rips the star apart atom by atom, leaving nothing behind but an expanding cloud of glowing debris. What makes these events so valuable to astronomers isn't just their violence, it's their predictability. Unlike other supernovae, which vary wildly in brightness, Type Ia explosions always release roughly the same amount of energy. That consistency turns them into cosmic yardsticks. By measuring how bright a Type Ia supernova appears from Earth, scientists can calculate its distance with remarkable precision. It's like knowing the exact wattage of a light bulb in space. The dimmer it looks, the farther away it must be. This technique helped astronomers make one of the most groundbreaking discoveries of the 20th century, that the universe's expansion is accelerating, driven by a mysterious force we now call dark energy. Without these stellar explosions as reference points, we might never have uncovered one of cosmology's deepest secrets. But Type Ia supernova aren't just measuring tapes, they're also cosmic forges. The violence of these explosions creates elements heavier than iron, from cobalt to nickel to gold, scattering them across interstellar space. Every time one of these supernovae erupts, it seeds future generations of stars and planets with the building blocks of everything from smartphone circuitry to human blood cells. In fact, much of the gold in your jewelry likely formed in the heart of a dying white dwarf billions of years ago, blasted across the galaxy in a supernova's shockwave. Their impact doesn't stop there. These explosions sculpt galaxies in ways we're only beginning to understand. The energy released can trigger star formation in nearby gas clouds, while the heavy elements they produce alter the chemistry of entire galactic neighborhoods. Some researchers even speculate that a nearby Type Ia supernova could have influenced Earth's climate in the distant past, leaving subtle traces in ancient rock layers. From cosmic yardsticks to elemental factories to galactic landscapers, these explosions prove that even in death, white dwarfs remain some of the universe's most dynamic architects. Yet mysteries linger. Recent observations have revealed unexpected variations in some Type Ia supernova, hints that the classic white dwarf plus companion scenario might not be the only path to explosion. Some could arise from mergers between two white dwarfs, while others might involve exotic mechanisms we haven't yet imagined. Each new discovery peels back another layer, showing us that these cosmic explosions, for all their predictability, still have secrets left to share. The death of a star isn't the end, it's a cosmic homecoming. When a white dwarf sheds its outer layers or explodes as a supernova, it doesn't just vanish. Instead, it scatters its enriched remains across space, seeding the interstellar medium with the very ingredients needed to birth new stars and planets. Picture a vast stellar nursery, its swirling clouds of gas and dust shimmering with potential. Without the recycled material from white dwarfs, those clouds would lack critical elements like carbon, oxygen, and nitrogen, the building blocks of rocky worlds and even life itself. Every atom forged in a white dwarf's heart becomes part of an endless cycle, a celestial conveyor belt where death fuels new creation. Take carbon, for example. Inside a white dwarf's core, helium fuses into carbon under immense pressure, creating an element essential for everything from DNA to diamonds. When a Type Ia supernova detonates, it catapults this carbon into the void, where it mingles with hydrogen and helium in interstellar clouds. Over millions of years, gravity pulls these enriched clouds together, compressing them until new stars ignite stars that now carry traces of their ancestors. Our own sun likely formed from a nebula peppered with debris from long-dead white dwarfs, meaning the carbon in your body might have once been part of a stellar relic that shone billions of years before Earth existed. Oxygen plays an equally vital role. White dwarfs rich in oxygen, a byproduct of helium fusion, release it into space through gentle stellar winds or violent explosions. This oxygen becomes the breath of future planetary systems, binding with hydrogen to form water or combining with metals to create minerals. In the Orion Nebula, astronomers have detected vast reservoirs of water vapor swirling around newborn stars, their oxygen almost certainly inherited from generations of white dwarfs. It's a humbling thought. The water in your glass might have once been part of a dying star's final gift to the cosmos, but the recycling doesn't stop there. White dwarfs also contribute heavier elements like neon, magnesium, and even traces of iron materials that shape the architecture of planetary systems. These elements act as cosmic glue, helping dust grains stick together to form asteroids, comets, and eventually planets. Without them, the universe would be a far simpler place, filled with gas giants and barren worlds, but lacking the chemical diversity that makes rocky, life-friendly planets possible. The very existence of Earth, with its iron core and silica-rich crust, owes a debt to white dwarfs that died long before our solar system was born. This grand cycle of matter has profound implications for galaxy formation. Over billions of years, generations of white dwarfs have enriched galaxies with heavier elements, altering how stars form and evolve. Early galaxies, born from pristine hydrogen and helium, produced massive, short-lived stars. But as white dwarfs and other stellar remnants polluted the cosmos with heavier elements, later generations of stars grew smaller, cooler, and more stable, creating the perfect conditions for planets and ultimately life. The Milky Way's spiral arms, its habitable zones, even the distribution of its star clusters, all bear the fingerprints of this gradual enrichment. What's truly astonishing is the scale of this process. Astronomers estimate that in our galaxy alone, white dwarfs inject thousands of Earth masses of heavy elements into the interstellar medium every year. Over billions of years, this steady drizzle of stardust has transformed the universe from a monotonous sea of hydrogen into a rich tapestry of elements, compounds, and possibilities. The next time you look up at the night sky, remember, you're not just seeing stars, you're witnessing a cosmic economy where matter is never wasted, only reborn. Most white dwarfs fade quietly, their magnetic fields no stronger than Earth's, but some defy expectations, wielding forces millions of times more powerful. These magnetic white dwarfs are cosmic anomalies, their surfaces crackling with invisible energy capable of shredding atoms and bending light. Imagine a stellar remnant where the magnetic pull is so intense it distorts the very shape of electrons, creating an environment unlike anywhere else in the universe. The origins of these extreme fields remain one of stellar astrophysics' most tantalizing puzzles. One leading theory suggests they're forged in stellar mergers, cataclysmic collisions between two white dwarfs. When these dense objects spiral into each other, their combined rotation could amplify pre-existing magnetic fields, like a cosmic dynamo spinning up to unimaginable strength. Alternatively, some fields might be fossilized, remnants of magnetism from the star's earlier life, preserved as the outer layers peeled away. Recent simulations show mergers could even generate entirely new magnetic fields through turbulent plasma motions, as if the violence of the collision imprinted a magnetic scream into the surviving core. These fields don't just sit idly, they transform their surroundings. In a typical white dwarf, heavy elements sink beneath the surface within centuries, but magnetic fields act like invisible cages, trapping ions in their grip. This creates bizarre atmospheric patches where metals like iron pool near the magnetic poles, visible as shifting spectral lines as the star rotates. Some magnetic white dwarfs even emit polarized light, twisting photons into spirals as they escape the star's ferocious influence. Then there's the matter of accretion disks. When a magnetic white dwarf pulls material from a companion star, the field channels the incoming gas into columns that slam onto the surface near the poles, generating X-ray hotspots brighter than entire galaxies. These aren't gentle cosmic processes, they're stellar tempests, where matter falls not in a steady rain but in focused, violent jets. But magnetic white dwarfs aren't the only outliers. Some stellar remnants defy categorization entirely, like the so-called hot DQ white dwarfs, objects so carbon-rich they challenge our understanding of stellar evolution. Others pulsate with rhythmic brightness variations, their interiors vibrating like struck gongs. Each oddity offers a new clue about the diversity of stellar deaths, proving that even in their final act, stars refuse to follow a single script. What unites these exotic varieties is their power to rewrite cosmic rules. Whether through magnetism, composition, or behavior, they remind us that the universe thrives on exceptions, and it's often in the outliers that the most profound truths are hiding. Not all white dwarfs fade silently. Some pulse with rhythmic beats, like cosmic metronomes keeping time across the galaxy. These pulsating white dwarfs are nature's gift to astronomers, their subtle brightness variations acting as Morse code from the stellar grave. Every flicker, every slight dimming and brightening carries secrets about what lies beneath their dense surfaces. It's as if the stars themselves are whispering to us, their vibrations revealing the hidden architecture of their cores. At the heart of this discovery is a technique called asteroseismology, the study of stellar vibrations. Just as geologists use earthquakes to map Earth's interior, astronomers analyze the pulsations of white dwarfs to probe their internal structure. Each oscillation pattern corresponds to specific layers and densities inside the star, creating a sort of seismic fingerprint. By measuring these tiny fluctuations in light, sometimes as small as 1%, scientists can reconstruct the white dwarf's composition, temperature, and even its cooling history with astonishing precision. The most famous pulsating white dwarfs belong to a class called ZZ Ceti stars, named after their prototype in the constellation Cetus. These stars pulsate due to a delicate balance between gravity and pressure in their outer layers, where hydrogen atoms ionize and recombine in a cyclical dance. The resulting vibrations create standing waves that ripple through the star, each frequency corresponding to a different internal depth. It's like tapping a glass to hear its pitch, except in this case, the glass is a stellar remnant light years away, and the pitch tells us whether its core is crystallizing or still fluid. One of the most intriguing revelations from these pulsations is the discovery of core crystallization. As a white dwarf cools over billions of years, the carbon and oxygen in its core can solidify into a lattice, much like water freezing into ice. This phase transition releases latent heat, slowing the star's cooling rate and leaving a distinct signature in its pulsation patterns. Asteroseismology has allowed astronomers to estimate that some white dwarfs may already have cores that are up to 90% crystallized, transforming them into celestial diamonds the size of Earth. But the vibrations don't just reveal the present, they also encode the past. The way a white dwarf pulsates depends on its mass, and mass is shaped by the star's life before collapse. A pulsation pattern dominated by high-frequency modes might indicate a thinner hydrogen layer, suggesting the star shed more of its outer material during its red giant phase. Slower, deeper pulsations could point to a more massive core, hinting at a progenitor star that burned hotter and faster. Even the presence of trace elements like helium or metals can alter the pulsation spectrum, offering clues about the star's diet, whether it ingested planetary debris or binary companions. Perhaps the most extraordinary aspect of these stellar heartbeats is their longevity. Some pulsating white dwarfs have been oscillating for billions of years, their rhythms barely slowing as they cool. That means the vibrations we detect today might have begun when Earth's continents were still forming, a cosmic echo stretching across geologic time. By listening to these ancient rhythms, we're not just studying dead stars, we're unraveling the life cycles of the universe itself, one pulse at a time. Some of the most dramatic cosmic events unfold when white dwarfs don't travel alone. In binary systems where two stars orbit each other, these stellar remnants become unpredictable actors, sometimes thieves, sometimes bombs, always rewriting the rules of stellar evolution. Picture a cosmic dance where one partner is a dense, fading ember and the other might be a bloated red giant or a vibrant main sequence star. Their gravitational tango can span centuries or mere hours, depending on how close they spiral, but the consequences are always profound. Take cataclysmic variables binary systems where a white dwarf siphons gas from its companion. Like a vampire of the cosmos, the white dwarf's gravity strips hydrogen-rich material from the outer layers of its neighbor, funneling it into a glowing accretion disk. This stolen matter doesn't just vanish, it spirals inward, heating to millions of degrees until it crashes onto the white dwarf's surface. The result? Periodic outbursts called nova, where the accumulated hydrogen ignites in a thermonuclear firestorm, briefly outshining the combined light of both stars. Unlike supernova, these explosions don't destroy the white dwarf. They're cosmic resets, clearing the slate until the theft begins anew, but sometimes the theft goes too far. If a white dwarf in a binary system pulls enough material to cross the Chandrasekhar limit, about 1.4 times the mass of our Sun, it doesn't just flare. It detonates. The runaway fusion reaction tears through the star's core in seconds, unleashing a Type Ia supernova. These explosions are so uniform in brightness they're used as cosmic measuring tapes, revealing the expansion rate of the universe itself. What makes them extraordinary is their predictability. The same process, mass stealing followed by catastrophic collapse, happens the same way every time, making them indispensable tools for cosmology. Binary systems also offer a front-row seat to stellar cannibalism. In some cases, the white dwarf's gravity distorts its companion into a teardrop shape, stripping it layer by layer until only a planetary mass core remains. Other systems, like the famous Sirius pair, showcase a more balanced but equally eerie dynamic, where the white dwarf's faint glow contrasts starkly with its brilliant sibling. These pairings are gold mines for astronomers, providing real-time laboratories to study mass transfer, magnetic fields, and the violent end stages of stellar life. The future of these duos is anything but quiet. Over millennia, gravitational waves will cause their orbits to decay, pulling the stars closer until they either merge or trigger another explosion. Some may become ultra-compact binaries, whirling around each other in minutes. Others might collapse into neutron stars or black holes, their fate sealed by the balance between accretion and explosion. What makes these systems so invaluable is their transparency. Unlike solitary white dwarfs, whose histories must be pieced together from subtle clues, binaries lay their dynamics bare. Every flare, every flicker, every trace of stolen matter in their spectra tells a story, one that's still being written, with each orbit adding another line to the cosmic script. Few cosmic events match the raw spectacle of two white dwarfs colliding, a celestial ballet where gravity writes the final act. Picture these dense stellar remnants locked in a death spiral, orbiting each other hundreds of times per second as they lose energy through gravitational waves. In their final moments, they merge in an explosion of light and energy, sometimes unleashing a supernova brighter than a billion suns. These collisions are among the rarest phenomena in the universe, occurring perhaps once every 10,000 years in a galaxy like ours. Yet when they happen, they rewrite the rules of stellar physics. The aftermath depends entirely on the combined mass of the merging pair. If their total stays below the Chandrasekhar limit around 1.4 solar masses, they might form a single, more massive white dwarf, reigniting nuclear fusion in a temporary, born-again phase. But if their combined mass tips over that threshold, the result is far more violent, a Type Ia supernova, the very kind used to measure cosmic distances. These explosions are so uniform in brightness they've become the gold standard for probing the expansion of the universe. What makes white dwarf mergers unique is their role as cosmic chemists. Their explosions forge heavy elements like iron, nickel, and even gold, scattering them across interstellar space. Simulations reveal the breathtaking dynamics of these collisions. Supercomputer models show how the less massive white dwarf is torn apart first, its material forming a swirling disk around its companion before both cores merge. The heat and pressure trigger runaway fusion, detonating the star in a fireball visible across the cosmos. Observational evidence supports these models. In 2016, astronomers spotted a supernova named Assassin 15LH that shone twice as brightly as typical Type Ia events, suggesting it originated from a white dwarf merger where both stars were already near the mass limit. But not all collisions end in destruction. Some mergers produce exotic stellar remnants unlike anything else in the universe. A pair of oxygen neon white dwarfs might collapse into a neutron star, their combined gravity overwhelming electron degeneracy pressure. Others could form highly magnetic white dwarfs, their fields amplified by the turbulent merger process. There's even speculation that certain ultra-dense white dwarfs, ones that inexplicably surpass the Chandrasekhar limit without exploding, might be the products of past mergers, their stability defying current theories. The mysteries surrounding these events are as compelling as the explosions themselves. Why do some mergers result in supernova while others form stable remnants? How often do these collisions produce magnetars or neutron stars instead of white dwarfs? And could there be an entire population of hidden merger remnants masquerading as ordinary stars? Each unanswered question reminds us that white dwarfs, even in their final moments, are far more than dying embers. They're the architects of cosmic transformation, their collisions shaping the universe in ways we're only beginning to understand. Every white dwarf is on an unfathomably slow journey toward darkness, a cooling process measured not in billions but trillions of years. These stellar embers radiate away their remaining heat with glacial patience, their surfaces dimming degree by imperceptible degree. Given enough time, far more than the current age of the universe, they'll fade completely, becoming cold, inert spheres known as black dwarfs. The irony is profound. These future objects, the universe's final stellar fossils, don't yet exist. Even the oldest white dwarfs, formed when galaxies were in their infancy, haven't had time to cool past a few thousand degrees. The cosmos simply hasn't been around long enough for the first black dwarf to emerge. Theoretical models paint a haunting picture of these ultimate stellar remnants. A black dwarf would retain the mind-bending density of a white dwarf, a sun's mass compressed into an Earth-sized sphere, but with no light or heat left to give. Its carbon-oxygen core, once a seething plasma, would have crystallized into a lattice more perfect than any diamond, its atoms vibrating just barely above absolute zero. No fusion, no magnetic fields, no stellar winds, just pure gravitational presence, so dark it would be nearly impossible to detect against the void of space. The only way to spot one would be through its subtle gravitational influence on nearby objects, bending starlight like a ghostly lens or tugging at passing comets with invisible fingers. Yet even this cold fate isn't absolute. Quantum mechanics suggests black dwarfs might still undergo rare, slow transformations, over timescales that make the current age of the universe seem like a blink. Protons, the building blocks of atomic nuclei, could theoretically decay. If this phenomenon occurs, black dwarfs would gradually evaporate into subatomic particles, their immense mass dissolving into the quantum foam of spacetime. Other theories propose that in a universe dominated by dark energy, black dwarfs could be the last structures left before cosmic expansion tears all matter apart. They'd outlive galaxies, outlive star formation, even outlive the black holes that now seem eternal, only to face their own quiet dissolution in the universe's final moments. What makes black dwarfs so compelling isn't just their hypothetical properties, it's what they reveal about the limits of our knowledge. Modern astrophysics can model their formation, but the timescales involved are so vast they defy intuition. We understand stellar evolution in snapshots, piecing together a cosmic movie from scattered frames. The full story of black dwarfs stretches into realms beyond observation or experiment, where theories must stand on mathematical elegance alone. Even our best telescopes can't peer into that distant future. We're left with equations and imagination, projecting forward from the behavior of today's white dwarfs. This cosmic long view forces us to confront how little we truly know about the universe's ultimate fate. Will black dwarfs be the last witnesses to a cold, expanding emptiness? Or will quantum effects or undiscovered physics rewrite their destiny? For now, these questions linger at the edge of science, a reminder that even the quietest stars still have mysteries to tell. Peering into the faint glow of white dwarfs requires instruments at the very edge of technology, eyes sharp enough to dissect light from a dying ember across light years of space. The Hubble Space Telescope revolutionized this pursuit, its crystal-clear vision free from Earth's atmospheric distortions, capturing details no ground-based telescope could match. Hubble's ultraviolet capabilities were particularly transformative, revealing heavy metals like titanium and chromium in white dwarf atmospheres, elements that shouldn't linger on the surface unless these stars were actively consuming planetary debris. One landmark study of the white dwarf G238-166 found its atmosphere polluted with vaporized rock, offering the first direct evidence of a shredded asteroid orbiting a dead star. Then came the James Webb Space Telescope, pushing the boundaries further into the infrared. Where Hubble saw traces, Webb detects entire chemical inventories. Its spectrographs can identify not just elements but molecules, water vapor, carbon dioxide, even complex hydrocarbons in the atmospheres of white dwarfs that swallowed icy worlds. In 2023, Webb's observations of WD0856 plus 334 revealed a bizarre mix of neon and oxygen, suggesting this star might have cannibalized a planet with a composition utterly alien to our solar system. The telescope's sensitivity to heat also lets it study older, colder white dwarfs previously invisible to Hubble, expanding our census of these stellar fossils into uncharted cosmic eras. But the future holds even greater promise. The European Space Agency's Gaia mission, while not exclusively focused on white dwarfs, has mapped over 300,000 of them with unprecedented positional accuracy, revealing subtle wobbles that hint at unseen planets or companion stars. Upcoming missions like NAS and Nancy Grace Roman Space Telescope will take this further, using microlensing to detect Earth-mass planets orbiting white dwarfs worlds that might have migrated inward after their star's death. Meanwhile, the Vera C. Rubin Observatory's decade-long legacy survey of space and time will catch fleeting events like white dwarf nova and mergers in real time, transforming our understanding of these stars' violent final acts. The most tantalizing prospects lie in proposed missions like ESA's Pluto, designed to spot transiting planets around white dwarfs, or NAS, a habitable worlds observatory, which could analyze the atmospheres of any surviving worlds for signs of life. Imagine confirming a planet with oxygen-rich air and water vapor orbiting a white dwarf, proof that biology can outlast stellar death. Why does this matter beyond scientific circles? Because white dwarfs are mirrors reflecting our own cosmic future. Every breakthrough in understanding their planetary systems, their chemistry, or their explosive deaths informs what awaits Earth billions of years hence. Public interest fuels these missions, taxpayer funding, citizen scientists classifying white dwarf spectra, even amateur astronomers tracking their brightness variations. When we invest in studying these stellar relics, we're not just exploring the past, we're preparing for humanity's ultimate fate among the stars. White dwarfs aren't just studied by scientists in lab coats. Some of the most groundbreaking discoveries have come from everyday stargazers armed with nothing more than a computer and curiosity. Projects like Zooniverse's White Dwarf Zoo have turned cosmic detective work into a global collaboration, where volunteers sift through telescope data to identify these faint stellar remnants. In 2018, a retired schoolteacher combing through images flagged an unusual white dwarf with a bizarre light pattern. It turned out to be a rare type pulsing with rhythmic brightness changes, a find that professional astronomers had overlooked in their automated scans. The beauty of citizen science lies in its simplicity. Volunteers don't need advanced degrees, just a keen eye and patience. One standout discovery came from a teenager in Norway who noticed a white dwarf with odd spectral lines while classifying data on the Backyard Worlds platform. Follow-up observations revealed it was surrounded by a disk of shattered planetary material, offering direct evidence of a rocky world torn apart by the star's gravity. These contributions aren't just footnotes. They've reshaped catalogs, leading to the identification of hundreds of previously unknown white dwarfs, including exotic binaries and candidates with potential planetary debris. What makes these efforts so vital is scale. Professional telescopes generate more data than researchers can possibly analyze alone. By crowdsourcing the work, projects tap into a collective intelligence that's unmatched, like having thousands of extra pairs of eyes scanning the cosmos. The Galaxy Cruise Initiative, for example, lets participants track how white dwarfs move through different galactic regions, revealing clues about the Milky Way's history. It's a reminder that the universe doesn't belong solely to academics. Its secrets are there for anyone willing to look. The cultural imprint of white dwarfs stretches far beyond research papers. These stars have inspired everything from sci-fi novels to philosophical musings about time and entropy. In The Hitchhiker's Guide to the Galaxy, a white dwarf named Magrathea serves as the backdrop for a planet-building factory, playing on their role as cosmic recyclers. Artists visualize them as ghostly orbs in deep space paintings, symbols of endurance in a transient universe. Even music echoes their themes. Electronic duo The Orbs sampled radio emissions from a pulsating white dwarf in their track Little Fluffy Clouds, blending science with sound. This intersection of science and culture underscores a deeper truth. White dwarfs aren't just celestial objects. They're mirrors reflecting humanity's hunger to understand time, legacy, and our place in the cosmos. Whether through a volunteer's discovery or a songwriter's tribute, these stellar remnants remind us that the universe's story is still being written, and everyone's invited to contribute a line. White dwarfs have long captivated storytellers, their eerie glow and unfathomable density making them perfect backdrops for science fiction's most mind-bending concepts. Take the iconic Stargate from Stargate SG-1. While never explicitly stated, the wormhole network's stability hints at exotic physics reminiscent of white dwarf degeneracy pressure, where matter is compressed to its ultimate limit. Then there's Interstellar, where the crew navigates a system anchored by a dying star, its gravitational lensing bending light like a cosmic magnifying glass. Though the film uses a black hole for its climax, the visuals echo real phenomena observed around white dwarfs, where light warps just enough to distort the view of anything orbiting too close. Video games, too, exploit their otherworldly potential. In Destiny 2, the alkaline dust mission unfolds on a derelict spaceship caught in the pull of a white dwarf, its hull buckling under tidal forces as players scramble to escape. The game's artists nail the aesthetic, a blue-white orb no larger than a moon, yet weighing more than a sun, its surface etched with cracks of crystallized carbon. Even Mass Effect toys with the idea, suggesting advanced civilizations might harness white dwarfs as energy sources, their slow cooling tapped like a galactic battery. What's fascinating is how often fiction stumbles onto real science. The Doctor Who episode, The Impossible Planet, features a base orbiting a white dwarf suspended above a black hole's event horizon. While the scenario is exaggerated, the gravitational interplay mirrors actual binary systems where white dwarfs and black holes dance in close proximity. Similarly, Larry Niven's Ringworld novels imagine entire civilizations thriving in the habitable zone of a white dwarf, a concept astronomers now consider plausible for second-generation planets. Yet for all their creative liberties, these stories share a kernel of truth. White dwarfs do warp space-time, just not as dramatically as black holes. They can host planets, though surviving ones would be scorched relics, and their crystalline cores, those are real, two carbon lattices forming over eons like diamonds the size of worlds. The line between science and fiction blurs when you realize these stellar remnants are stranger than any scriptwriter's wildest draft. Perhaps the most poignant fictional use comes from The Time Machine by H.G. Wells. In the distant future, the protagonist witnesses a dying sun, a red giant collapsed into a black cinder, orbiting a cooling ember. Wells imagined this as the heat death of the universe, but today we recognize it as a prescient description of white dwarfs fading into black dwarfs. His vision, written decades before their discovery, accidentally predicted their role as the universe's final tombstones. This interplay between fact and fantasy isn't just entertaining, it's educational. When The Expanse depicts a white dwarf's accretion disk glowing like molten sapphire, it sparks curiosity about real systems like Mira B, where a companion star feeds material onto a dead core. When Star Trek uses one as a temporal anomalies anchor, it echoes real research into how extreme gravity bends time. By blending spectacle with scientific kernels, these stories become gateways, inviting audiences to explore the true wonders hiding in telescope data. The lesson here isn't just about white dwarfs, it's about humanity's need to mythologize the cosmos. We project our fears of mortality onto their cooling embers, our hopes for resilience onto their surviving planets. But the reality, as always, outshines the fiction. These stellar ghosts aren't just set pieces, they're active participants in the galaxy's story, their whispers carrying secrets about everything from planetary survival to the universe's ultimate fate. The next time you see one flicker on screen, remember, The truth is out there, waiting in the light of dying stars. One of the biggest misconceptions about white dwarfs is that they're simply cold stars, faded versions of what they once were. In reality, they're something far stranger. A white dwarf isn't cooling because it's running out of fuel like a dying campfire. It's already burned through all its nuclear fuel, and what we're witnessing is the slow release of stored thermal energy, like a cosmic battery discharging over billions of years. These stellar remnants are still scorching hot, with surface temperatures often exceeding 10,000 degrees Celsius hotter than some active stars. Their faint glow isn't a sign of weakness, but a consequence of their tiny size. Pack all that heat into an object no bigger than Earth, and it simply can't shine as brightly as its former self. Another persistent myth is the confusion between white dwarfs and black holes. While both are in points of stellar evolution, they're separated by an enormous gap in mass and physics. A white dwarf forms when a star like our Sun gently sheds its outer layers, leaving behind a dense core held up by quantum mechanical pressure. Black holes, on the other hand, are born from the violent collapse of stars many times more massive, where gravity overwhelms all known forces. The difference is like comparing a marble to a bottomless pit. One is incredibly dense but still made of familiar matter, while the other warps space-time itself. Perhaps the most poetic misconception is that white dwarfs are dead stars. True, they no longer fuse elements in their cores, but they're far from inert. These stellar embers continue to shape their surroundings, whether through gravitational interactions, accretion of planetary debris, or eventual explosive rebirths as supernovae. Their magnetic fields can be millions of times stronger than Earth's, creating invisible structures in space that defy imagination. Some even pulsate with rhythmic precision, vibrating like cosmic tuning forks. This isn't death, it's a new phase of stellar existence, one we're only beginning to understand. Why does accurate public understanding matter? Because white dwarfs aren't just celestial curiosities. They're critical tools for measuring cosmic distances, studying galactic history, and even probing the ultimate fate of our universe. When people imagine them as cold, dead husks, they miss the extraordinary reality. These objects are dynamic laboratories for extreme physics, archives of galactic evolution, and potential havens for future life. Misconceptions don't just distort facts, they blind us to the universe's true wonders. Consider how white dwarfs revolutionized our view of dark energy. The discovery that distant Type Ia supernova exploding white dwarfs were fainter than expected led to the shocking realization that the universe's expansion is accelerating. If the public had dismissed these stellar remnants as irrelevant cosmic relics, one of modern astronomy's greatest breakthroughs might have lacked the cultural impact needed to drive further exploration. The truth about white dwarfs is more fascinating than any myth. They're not in points, but transformers, stellar alchemists turning destruction into creation, chaos into records, and death into new possibilities. When we correct misconceptions, we're not just teaching science, we're opening eyes to the universe's endless capacity to surprise. White dwarfs may seem like isolated relics, drifting silently through the void, but they're actually deeply woven into the universe's grand architecture. Picture the cosmic web, that vast, intricate network of galaxy clusters connected by glowing filaments of gas, with dark matter threading through it all like invisible scaffolding. Within this web, white dwarfs serve as both tracers and sculptors, their distribution revealing hidden patterns in the cosmos, while their eventual demise enriches the interstellar medium with heavy elements. Take the way these stellar remnants cluster around galaxies. In massive elliptical galaxies where star formation ceased long ago, white dwarfs dominate the stellar population. Their collective glow contributes to the diffuse light that fills galactic halos, a phenomenon astronomers call intracluster light. This ghostly illumination isn't just aesthetic, it's forensic evidence of galactic cannibalism, the remains of smaller galaxies torn apart and absorbed over billions of years. The white dwarfs from those devoured systems now orbit freely between stars, silent witnesses to the violent mergers that shaped modern galaxies. Their influence extends far beyond visible light. When white dwarfs in binary systems explode as Type Ia supernova, the shockwaves ripple through the cosmic web, heating intergalactic gas and preventing it from collapsing into new stars too quickly. These explosions are cosmic regulators, controlling the pace of galaxy evolution by injecting energy into the universe's largest structures. Some researchers even speculate that without supernova from white dwarfs, galaxy clusters would have formed differently, perhaps with denser cores and fewer spiral arms. Then there's their role as chemical propagators. Every white dwarf that sheds its outer layers or detonates as a supernova disperses carbon, oxygen, and heavier elements into the cosmic filaments, the rivers of gas connecting galaxy clusters. Over time, this enriched material flows into new galactic environments, seeding future generations of stars and planets with the ingredients for rocky worlds and organic chemistry. The calcium in your bones, the iron in your blood, even the gold in your jewelry likely passed through multiple white dwarfs before being incorporated into our solar system. Yet for all we've uncovered, white dwarfs still guard profound cosmological mysteries. Their distribution in galaxy clusters doesn't always match predictions, hinting at gaps in our understanding of dark matter's influence. Some ancient white dwarfs appear too cool for their estimated ages, suggesting unknown physics in their crystallization process, and the very nature of Type Ia supernova, those critical cosmic yardsticks, remains debated. Are they all triggered by white dwarfs stealing mass from companions, or do some arise from collisions between two white dwarfs? The answer could recalibrate our measurements of the universe's expansion rate. Perhaps most tantalizing is their potential connection to dark energy. If the properties of white dwarfs change subtly over cosmic time, perhaps in their cooling rates or explosion mechanisms, they might hold clues about this mysterious force driving the universe apart. Future telescopes could use white dwarfs as probes, measuring how dark energy's influence varies across different galactic environments. These stellar ghosts are more than endpoints, they're active participants in shaping the universe's largest structures, their quiet lives and explosive deaths echoing across billions of light years. Every new discovery peels back another layer, revealing how deeply interconnected cosmic scales truly are, from the quantum physics inside a crystallized stellar core to the vast filaments of the cosmic web. The story isn't just about how stars die. It's about how their endings become the scaffolding for everything that follows. Even after decades of study, white dwarfs guard some of their most intriguing secrets, like cosmic vaults refusing to yield their treasures. Take their bizarre atmospheric compositions. Some contain heavy metals like calcium and iron that should have sunk beneath their surfaces eons ago. These unexpected elements float like stubborn dust motes in a sunbeam, defying models of gravitational settling. One leading theory suggests these metals might be cosmic crumbs, the vaporized remains of asteroids or even planets torn apart by the white dwarf's gravity. But why do some stars show these pollutants while others appear pristine? The answer could rewrite our understanding of planetary system survival rates around dying stars. Then there's the enigma of their magnetic fields. Most white dwarfs exhibit magnetism no stronger than Earth's, but a rare few, about 10%, generate fields millions of times more powerful. These stellar magnets shouldn't exist according to conventional models. One hypothesis proposes these extreme fields are fossilized remnants from the star's earlier life, preserved like a fly in amber as the outer layers blew away. Another suggests they're forged during stellar mergers, when two white dwarfs spiral together in a turbulent dance that amplifies magnetic energy like a cosmic dynamo. The truth might lie somewhere in between, hidden in the chaotic physics of collapsing stellar cores. Perhaps the most perplexing outliers are the carbon-rich, hot decay white dwarfs. These stars cloak themselves in atmospheres dominated by carbon instead of the usual hydrogen or helium, a composition that defies standard stellar evolution pathways. Did they originate from rare progenitor stars that burned differently, or are they the products of violent interactions that stripped away their outer layers, exposing nuclear burned material beneath? Their very existence challenges textbook narratives about how stars shed their envelopes before becoming white dwarfs. These mysteries aren't just academic puzzles, they're the compass needles guiding next-generation astronomy. The unexplained metal pollution in white dwarf atmospheres could reveal how often planetary material survives a star's death throes, informing the search for habitable worlds in aging systems. Unraveling magnetic field origins might expose new fundamental physics about how cosmic magnetism persists across eons, and those carbon-cloaked oddballs. They could represent an entirely overlooked channel of stellar evolution, forcing us to redraw the life cycle diagrams in astrophysics textbooks. What makes these gaps in knowledge so thrilling is their potential to overturn assumptions. Every anomalous white dwarf is a breadcrumb trail leading to deeper cosmic truths about how matter behaves under extreme conditions, how planetary systems evolve, even how galaxies distribute their heavy elements. Scientists aren't just studying fading stars, they're piecing together the universe's operating manual, one paradox at a time. And in that pursuit, the unanswered questions matter just as much as the solved ones, because they're the signposts pointing toward tomorrow's breakthroughs. White dwarfs might seem like unlikely detectives in the hunt for dark matter, but their very nature makes them perfect cosmic traps for this elusive substance. Picture a white dwarf's incredible density, its gravitational pull so strong that even particles of dark matter, which barely interact with normal matter, could get snared in its grip. Some theories suggest these stellar remnants could accumulate dark matter in their cores over billions of years, subtly altering how they cool. If dark matter particles collide and annihilate within a white dwarf, the energy released might slow its fading glow in ways that defy conventional models. This isn't just speculation. Researchers are actively scouring white dwarf cooling curves for anomalies that could betray dark matter's presence. One particularly compelling method involves microlensing, a phenomenon where a white dwarf's gravity bends light from a background star like a lens. If dark matter clumps around a white dwarf, the resulting distortion could create telltale fluctuations in that star's brightness. Projects like the Optical Gravitational Lensing Experiment, OGLE, have already used this technique to map invisible mass in our galaxy, and white dwarfs could be the next frontier. Imagine pinpointing a patch of sky where a white dwarf's lensing effect is slightly off, just enough to hint at an unseen halo of dark matter clinging to it. Then there's the tantalizing possibility of direct capture. Certain dark matter candidates, like weakly interacting massive particles WIMP, could become trapped in a white dwarf's interior, their collisions generating heat that delays the star's cooling. Astronomers have identified a handful of white dwarfs that are inexplicably warmer than their age suggests. Could dark matter be the invisible furnace keeping them alive? Experiments like the upcoming Legacy Survey of Space and Time LSST at the Vera C. Rubin Observatory aim to scan millions of white dwarfs for these thermal irregularities, turning them into a galaxy-wide dark matter sensor network. The connection goes even deeper. Some models propose that white dwarfs in dense regions like galactic cores where dark matter is thought to cluster might exhibit unique pulsations or chemical signatures if they're interacting with dark matter streams. It's a cosmic feedback loop. The same gravity that shapes dark matter's distribution could also make white dwarfs its most sensitive detectors. What makes this search so revolutionary is its simplicity. Unlike billion-dollar particle colliders, white dwarfs are natural laboratories, their behavior a readout of physics we can't replicate on Earth. Every anomaly, every unexpected flicker in their light could be a breadcrumb leading us closer to understanding the universe's missing mass. And in that pursuit, white dwarfs aren't just passive subjects, they're active collaborators, their silent glow illuminating one of science's greatest mysteries. This isn't just about dark matter, it's about how the universe's smallest clues, a star's cooling rate, a slight warp in starlight, can unravel its grandest secrets. White dwarfs remind us that the cosmos writes its truths in unexpected places, and sometimes the key to understanding the invisible lies in the light of the dead. Imagine a classroom where students aren't just reading about stars in textbooks, they're analyzing real data from white dwarfs, discovering planetary debris in their spectra, and even simulating stellar collisions on their laptops. This isn't science fiction, it's happening right now, thanks to innovative educational programs bridging cutting-edge astronomy with hands-on learning. Across the globe, initiatives are transforming these cosmic relics into dynamic teaching tools, proving that stellar evolution isn't just for astrophysicists. Take the Zooniverse platform's White Dwarf Zoo, where high schoolers help classify white dwarfs alongside professional researchers. By sorting through telescope images, students learn to identify unusual features, like the telltale metal pollution of a star consuming its planets while contributing to actual scientific papers. It's citizen science at its best, turning classrooms into research labs. For educators craving structured resources, NAS, a universe of learning program, offers ready-made lesson plans using white dwarfs to illustrate core concepts. One standout activity has students model the Chandrasekhar limit with marbles and foam boards, physically feeling how density and mass interact in collapsing stars. Another uses glow sticks to demonstrate how white dwarfs cool over time, the dimming light mimicking their trillion-year fade to black. Even art classes are getting involved, with projects where pupils paint planetary nebulae based on Hubble images, then debate how a star's composition shapes its final masterpiece. Universities are raising the stakes with tools like Open Space, an open-source planetarium software that lets students fly through 3D models of white dwarf systems. Picture a lecture where learners zoom into the turbulent accretion disk of a magnetic white dwarf, watching simulated gas spiral onto its poles in real time. Or MIT's Visualizing Stellar Life Cycles project, where VR headsets transport users inside a supernova explosion, standing atop a virtual planet as its dying sun swells into a red giant. These immersive experiences don't just teach facts, they forge emotional connections, making abstract concepts visceral. The impact extends beyond STEM. In humanities courses, white dwarfs serve as springboards for discussions about time, legacy, and humanity's place in the cosmos. English teachers use poetry penned by astronomers to explore how scientific discovery inspires art, while philosophy classes debate the ethics of future civilizations harnessing white dwarf energy. Even younger kids engage through storybooks like The Little Star That Could, where a white dwarf's journey personifies resilience, proving complex science can be made accessible at any age. What makes these efforts so vital isn't just the knowledge they impart, it's the perspective they offer. When a student realizes the atoms in their pencil might have been forged in a white dwarf's core, astronomy stops being a distant abstraction. It becomes personal, a reminder that we're all stardust grappling with the same cosmic mysteries. And with free resources like the American Astronomical Society's educator webinars or the European Space Agency's Dead Stars interactive modules, bringing the universe into the classroom has never been easier. This democratization of cosmic knowledge hints at something profound. The next groundbreaking discovery about white dwarfs might not come from a PhD in a mountaintop observatory, but from a curious teenager analyzing public data after school. By turning these stellar fossils into teaching tools, we're not just educating future scientists, we're nurturing a generation that sees the universe as a living, evolving story, one they're empowered to help decode. The stars belong to everyone, and white dwarfs, with their quiet brilliance and layered histories, are perfect guides to that shared inheritance. Let's tackle some of your burning questions about white dwarfs, starting with one we hear all the time: could we ever visit one? The short answer: not anytime soon. Even the closest known white dwarf, Sirius B, sits over 8 light-years away. At current spacecraft speeds, that's a journey lasting tens of thousands of years. But let's say we could get there, what would we find? A world of extremes. The gravity on its surface would crush you instantly, with a force over 300,000 times stronger than Earth's. And while it might look like a flickering diamond in the sky, its surface temperature rivals our sun, so you'd vaporize long before you could snap a selfie. Now, what about our own star's fate? Will the sun become a white dwarf? Absolutely, but don't panic just yet. In about 5 billion years, the sun will exhaust its hydrogen fuel, swell into a red giant engulfing Mercury, Venus, and likely Earth, then shed its outer layers to reveal a dense, Earth-sized core. That leftover ember, our sun's white dwarf phase, will glow faintly for trillions of years, a quiet monument to the solar system that once was. Here's another gem from the comments: can planets survive a star's transformation into a white dwarf? Surprisingly, yes, but it's a cosmic roller coaster. Outer planets like Jupiter or Saturn might endure the sun's red giant phase, only to face violent orbital shifts as the dying star loses mass. Some could be flung into deep space, others might spiral inward, torn apart by tidal forces. Yet recent discoveries hint at resilient worlds like the gas giant found orbiting a white dwarf 40 light-years away, proving planetary systems can outlast their star's deaths. And for the sci-fi fans asking, could life exist near a white dwarf? The odds are slim, but not zero. A planet would need to orbit incredibly close, about 100th Earth's distance from the sun, to stay warm. Tidal locking would leave one side scorched, the other frozen, with only a thin twilight zone offering refuge. But if life did cling on, it'd face another challenge. White dwarfs are stingy with energy. Their habitable zones shrink as they cool, forcing any survivors into a desperate migration inward over eons. These questions reveal something profound. White dwarfs aren't just relics, they're mirrors. In their fate, we see our own solar system's distant future. In their resilience, a testament to the universe's endless creativity. Every mystery we unravel about them adds another piece to the puzzle of cosmic evolution, and reminds us that even in the coldest corners of space, the story's never truly over. Now, as we wrap up, let's take one final look at why these stellar embers matter not just to astronomers, but to anyone who's ever gazed up at the night sky